lightning speed review from yesterday. See, look at all this stuff we did. Theoretically, the two problems that we're about to do are also in your packet. All right, it's important, I think, you'll know that this is true because you tried maybe a cone problem last night and didn't do so well. You might need this on the trough problem too. But this will help us with some guiding principles here. All right, this should be, am I right? This is like the next example in the packet that I gave you yesterday, the review, the note sheet, which is like a little bit fudgy. Yeah, there we go. I got it actually. Throw that away. You know what that was? Kind. Wasn't that kind? Was it France?
Oh yeah. Oh.
All right. So we have a cone here, and I don't know if you heard Katya's question about the warm up. Like she was like, wait, doesn't the height of the cylinder matter that we started with, or something like that? And like, not really, actually, right? And in fact, same here to some extent. Same thing here. Like actually, the thing that we're going to care about in this problem is how this water is behaving. The overall cone, we don't really care about the overall cone size. Like the fact that this is like 5 feet tall, like it could be 100 feet tall. The thing we care about is the little bit of water at the bottom. Except we maybe do care about the overall size of the cone for one particular thing, and we'll maybe come back to that in a second. All right, let's start writing things down that we know and write down an equation for the volume of a cone and all that kind of stuff. So let's do that. I think that we can all do that together. dv dt, I guess is what this is given. This part is kind of becoming old hat to us. What do we get? It has a height of 10 feet and a radius of 5 feet. I'm dubious to write that down as equal to like r or h or something right this very second. Honestly, 6 feet is what I care about right now. Do you want to call that h, I guess? Or d for depth? I don't know. We'll call it 6 though. We'll call it h. Okay. And then the only thing we'd like to know is how fast is the water level rising. So dh dt is the thing we seek. And notice, again, I haven't actually written down 10 feet or 5 feet yet. I think they will be important, but I'm not sure how yet. Okay. So the volume of a cone is, we already did this yesterday, right? 1/3 pi r squared h. Okay. So now here's the problem with it. This makes this trickier than the cylinder problem from the warm-up, right? As the water goes up here or down, all of the things change, right? It's not like the cylinder where we can guarantee that like, oh, the radius always stays the same. No, none of them stay the same. The radius changes, the height changes, and the volume changes. This makes it a little bit trickier than that second warm-up problem. So I'm going to maybe show you my favorite approach and then also show you that the thing you might have done first will work too. In fact, again, math works. We can do this a couple different ways. But the thing that maybe this is now useful to say about this is, like I told you that this is 6 feet. Say you wanted that the water in here is 6 feet. Say you wanted the current radius. Could you get it? What is it? What's the current radius of the water? If the overall container is 10 feet and 5 feet in radius, why does that help us, in fact? Even though we said that they're kind of throwaway numbers, and they are, but they do kind of help us understand, like what, for example, the current ratio is, or what current radius is. That's the wrong word. Go ahead.
The angle.
The angle, we could figure out the angle if we wanted. Yeah, what would the radius be? Yeah, right now the radius would be 3 feet, right? Why do you see that? Yeah, and they're always going to maintain that same ratio, right, of height to radius. In fact, you could write down a general statement about the height and the radius, right? How is the height related to the radius? Let's call those h and r now. H is equal to 2r. So I actually don't care about this, 10 feet, 5 feet. Really, that's throwaway. If it was 20 feet and 10 feet, that would be equally useful. The guiding thing that I don't want to throw away is that this is always true. Regardless of where we are, regardless of how things All these numbers might be not constant, true. But this relationship always holds, no matter what. So that's important, I think. In particular, it's important because maybe I can rewrite my equation so that it has only one independent variable on the right side. Wouldn't that be a nice thing to do? So let's do that. Let's choose the independent variable that perhaps we care about. If someone asked us about r, we would choose maybe to do something different. But I'd like to maybe have this as, how about, all in terms of h. So I'm going to actually solve this because I've got my eyes on the prize here. I'd like an equation that has h's in it. I'm going to actually try and rewrite everything with an h. So that's 1/3 pi times r. Oh wait, r is just h over 2 squared times h. And then let's clean this up. We have a little bit of work. We still haven't gotten to any calculus yet. Do you agree that this will be, well, what is that? Pi over 24 times h cubed?
No.
12.
No.
Sorry, I got carried away. I was testing you. All right, now we're ready to do some calculus. So we get, what is that, pi over 4 h squared dh dt. I mean, everything is just working out really just swimmingly now. We have dv dt, we have our current height, and we just need dh dt, so I don't know, you finish it off. Okay. Okay. Yeah, we'll do. We only have one, so we can finish off. What do we have here? I just was worried about the time. I want to make sure we get to some of your homework questions too. Oops. Are you liking having the units in there too? What's H6? Come out nice. Oh, actually this does really come out nice. They keep making these problems nice, right? That'll be 36 divided by 36 is it 1 over pi? I think it's 1 over pi. That's what I think. Feet squared, feet cubed divided by feet squared will be feet per minute here. Did you get 1 over pi? You can approximate that if you like, right? But is that cool? So that came out pretty nicely, actually. Okay, let's do the U-Haul here problem. All right, we got truck A, we got truck B. They're leaving from the same depot. One leaves east, one leaves north. Okay. This one's going 40 miles per hour over here. So we'll call this, I don't know, you want to call this side length A and this side length B? And then we're asking, it says in the end, it says how fast is the distance between the trucks changing? So we'd like to have the distance between the trucks marked in this picture somehow. All right, so that's the situation we're in. We should write down some of these things, maybe, once we know them. We have, eventually it's pretty clear that we have this relationship, right? A squared plus b squared equals c squared. And we even like the calculus here. We can take the derivative. But this does have a little bit of a different flavor than maybe the last one that involved the Pythagorean theorem. Because it's not immediately as obvious what the values of a, b, and c are, right? So can you tell me any of those things? Like where is A? What's the length A? It's not given in the problem what the length A is, but maybe it is, kind of.
Yes, it is.
Oh, maybe it is. What is it? 4y.
6 minutes and 45 minutes.
Yeah, so it's 1/10 of an hour and we're going 40 miles per hour, right? So Jack says he thinks this is 4 miles, right? Is that okay? So 40 miles divided by hours times 1/10 of an hour. He says that's 4 miles. I think I agree with him. And then similar reasoning gives B as, of course, what's B? 3 miles. We already have dA dt and dB dt. We've just discussed those. That's 40 and 30. All right. And the thing we seek is dC dt. There are so many things to keep track of here. We got 3 rates and 3 side lengths. Like the previous Pythagorean theorem one that we did. What do we still need in order to finally substitute into this related rates equation? What do we still need also? Looks like we have 6 things to plug into this equation, except for one, we need dC dt. But we're missing, we only have 4 things right now. Yeah, we need C also, right? What's C? What is it? Yeah, it's 5, right? There's only, so many times you can see Pythagorean triples before you can smell them a mile away, right? So plug these in. Again, maybe we'll just drop all the 2's. That's all for dC dt. Is that something we need to check? Do we need that right now, Jay? Is that 160 plus 90? Miles squared per hour equals 5 miles. So what do we get? We got 50 miles per hour. Okay, let's do a problem or two from. Oh, I wanted to say one more thing about any questions on this problem before I make it go away? I just want to make sure we're just trying to expose you to as many of these crazy problems as we can, and we will do a homework problem or 2 or 3 now. I've left about 15 minutes left still. I do want to show one more thing about the cone problem though. So is there any question on this slide before I go back to the cone one? Yeah, kiddies. I was hoping you'd ask that. You're like, wait a second, can we just skip all of this and be like 30, 40, 50, done, right? Is that, yeah, so in this particular problem, if you were to notice that subject to a whole bunch of interesting constraints, that this works in that situation, then yes, you'd be right. All right, but all we'd have to do is tweak this problem in a very small way, and suddenly none of that would work. Say this guy starts like a mile up this path from here. We'd still have everything working here, except that this would be, 4 miles instead. And then that wouldn't be right. You know what I'm saying? Like you could easily tweak this problem in such a way that suddenly it doesn't work. If they start at the same, let's see if we can get all the correct hedges on this. As long as they start in the right place, at the same place, and as long as, what else do we have to say? And maybe that's all we have to say. Do they start at the same place? At the same time. Yeah, at the same time. That's true. Another wrench in the works would be if one leaves a minute later than the other or something, right? Yeah, if they start at the same place at the same time though, then maybe you could just say it's 50 miles per hour. You're right.
No, I put it 1 hour 15 minutes.
But then you might ask,
I got it.
like, how could we prove that? And the answer is, well, you do the calculus. It's the proof. Like, but I don't know what proof you have. Maybe you could kind of think about. Yeah, I don't know. I'm trying to think about another rigorous way to prove that. Let me say something briefly about this problem. Hey guys, again, I think this provides a rich opportunity for you to see some nice connections. Notice on this one, guys, what if you did like kind of Johnny style on this and took the product rule right away of this? What would you get? In fact, actually, we wrote this on the previous page already. What would it be? It'd be 1/3 pi r squared dh dt. Stay with me here. Plus 1/3 pi, well, 2, how about 2/3 pi r dr dt h, right? Just using the product rule. Is that an okay way to say it? Now notice that this is a little bit trickier. It's not like one of these just goes away, does it? Neither of these is 0 this time. Can we still rescue ourselves here? Notice what we need here. We need, we have dv dt, so we'll like plug that in. Let's just keep track of the things we would need. We have well, we don't have r, but we could get it. What was r? What was r at the moment of interest? Stay with me, please. Yeah, it's going to be 3, so you had to solve for that, right? You had to be like, okay, well, if r is equal to h over 2, then it must be 3 here, right? So that's how we got that. dh dt was given, though. No, dh dt is the thing we're looking for. So we'll leave that blank. R is 3. H is given as 6 feet. So we're good, but how do we resolve this snag that we don't have drdt? What's drdt? Well, let's talk about the relationship between r and h for a second. Stay with me, guys, thanks. What's the relationship between r and h? Now, I know this looked like just kind of a little auxiliary equation off to the side, but actually, couldn't we just for fun differentiate that equation? Did you say that you wanted a relationship between drdt and dht?
Yeah.
Yes, you did. Okay. So it's an easy relationship. Just differentiate this, right? And now what could you plug in here? Well, right? And I promise this is not the way to do it. But I promise that this will work out to be the same, though, right? You like it? You see, I just want to make sure it all turns like we did in the warm-up today. That you understand that this is right and this is correct mathematics, okay? Do you see how this could have worked too? Again, I recommend that you use our this approach over here. Okay? All right. Now with that, let's look at a few problems from the packet that you'd like to. What were the hot ones?